Okay, today we're going to start looking at, well, we're going to look more at functions and arguments, but in particular at functions that take other functions as arguments. And we're going to be looking at modifiers. A review from last time, we're dealing with syntactic trees. And in syntactic trees, we have three different kinds of nodes in a tree. We have terminal nodes. Those are the nodes at the bottom of the tree that don't dominate anything else. We have non-branching nodes. Those are nodes dominating a single daughter node. And we have branching nodes. Branching nodes are nodes dominating two daughter nodes. We can illustrate that here. We've got a sentence node at the top, which is branching. It has its two daughter nodes, which are NP and VP. The NP node itself is non-branching. It dominates an N node, which is non-branching, which dominates John, which is the terminal node. We have the same thing over on the VP side with VP and V non-branching nodes and Smiles as a terminal node. And for each of these, we have a separate rule for what to do. For the terminal node, we go to the lexicon. We look up and see what's listed as our translation. So for John, we look it up and we see that it translates as the name John. For Smiles, we look it up and we see that it translates as a predicate, lambda x, smile x. For non-branching nodes, the translation is the same as the translation of its daughter node. The daughter node's meaning essentially gets passed up to the mother node. Finally, for branching nodes, the translation is determined using function application. One of the nodes is analyzed as a function. It applies to the other node as an argument. So in our simple example, we have the interpretation of John as the name John. The interpretation of Smiles is a function lambda x smile of x. Then our non-branching nodes tell us that those interpretations just get passed all the way up. The interpretation of the NP is the same as the interpretation of N, which is the interpretation of John, which we just saw is the name John. The translation of the VP is a translation of V, which is a translation of Smiles, which we just saw is lambda x smile of x. Then with branching nodes, the translation of the S node is the result of applying the translation of the VP node as a function to the translation of the NP node. That is, we take the lambda x smile of x, we apply it to John, and we get smile of John. Okay, so next thing we're going to start looking at is what we call vacuous expressions. Vacuous is a fancy word for empty, and in this case, it's in a sense empty of meaning that we mean. We're going to be looking in particular at expressions like is. Okay, so the word happy, we're saying, translates as lambda x happy of x. The word black as lambda x black of x. The word proud, lambda x, lambda y, proud y x. Okay. But what do we do now with is? The word happy already divides the world into those things that are happy and those things that are not. What does is add to that? Well, it does actually add something. It adds tense information. It says that the happiness that you're saying John has, for example, holds now at the time of speech. But we're ignoring tense. We're going to get to tense eventually, but until then, we're just pretending that there is no tense. So what about the rest? It's a tensed form of be. Does be add anything? And it's at least plausible, at least possible, to say that be adds nothing. That its only job is to pass on the content of the adjective below it and to add tense. And since we're ignoring tense, there's nothing left to really do except pass on the adjective meaning. So that tells us that essentially is happy translates as the same thing that happy translates as. And we know what happy is, that's here. And for some reason, it doesn't let me do what I want to do. And so the question is, what do we do with is at the bottom here? Okay. We want it to be vacuous, but it is a word. You can't just ignore it. You have to do something with it. So if we look at it in tree form, the tree form looks like this. We have is here as a verb that has to combine with happy here, and the whole thing has to be a verb phrase. The verb phrase as a whole is something that has to be true or false of John, and so we know that the verb phrase is going to be of type ET. Happy, we've already seen, is a function that takes an individual, like John, and gives back a truth value. Its type is ET as well. So what is the possible types over here for the verb is? These are going to be the same, okay, whatever they are. But what exactly? Well, there's one formal possibility that would at least fit with going together with an ET type AP. That is, we could take the AP to be the function. It requires a type E, so we could think of maybe that would be type E. But that doesn't work because an AP that takes an E-type expression gives back a T-type expression. And the verb phrase is not a T-type expression. It's a type ET expression. So that basically tells us we cannot take the AP to denote the function that applies to the verb is as its argument. This is going to have to be some other type. And we do have another option open. Okay, anytime we put two things together by function application, one has to be the function and the other has to be the argument. But there's nothing saying that a function itself, like the AP over here, can't act as an argument instead of as the function. So what do we get if AP is the argument and is the function? What is the type of is in that case? Well, it has to take an ET expression as its argument, and it has to give back another ET expression. With that information, we can go ahead and answer the question. It looks like this. Is type ET. Okay, and I've repeated that type here, ET. And I've also spelled it out using this notion, this sigma tau labeling. Because when we defined function application, we used sigma and tau as our variables. And we said one thing is of type sigma tau and the other is of type sigma. When that happens, then we can combine the two together and we get something else of type tau, okay? So this just helps to match up what the sigma is and what the tau is. Here, the sigma on the verb phrase is type ET. That's this ET. Here, the tau on the verb is also of type ET, and that is the resulting ET up here. So if we can find an analysis of is of this type, something that takes an ET, a one-place predicate, and gives back an ET type, another one-place predicate, then we have something that will work in terms of the semantic types for putting the verb is together with the adjective happy. So the easiest thing to do is this. You see that is takes a predicate. That's what the lambda p is telling us. And it gives back that exact same predicate. No change. Just takes it and gives it right back. And we want p to be of type ET. That means it's going to take something of type ET, and it's going to give that same thing of type ET back. This type information here that says where p is of type ET, from now on, I'm going to put that here onto the lambda expression. This is not a change in what the lambda expression is doing. It's simply helping us see explicitly what the type is intended as for any particular function, right? Because after a lambda, we can put any kind of a thing here. We've put lambda x before, if that was a type E. We can also put a p, which is here of type ET, and we can put other things as well, as we will see later. So this is a function that takes some one place predicate p and gives back that same p. Since we already have the information here that p is a one place predicate, we don't need to also put it on there. We could, it wouldn't hurt. It would make for very messy representations. We'd have a lot of extra things that we didn't need to have. And so we don't actually put it there. Okay. So let's go now and look and make sure that we get the result back that we want. We now have analyzed is as a function that can take the translation of happy as its argument. So we take is happy and we analyze it by is being the function applied to happy as the argument. We just gave this lambda pp as the translation of is. So we just go ahead and put that there. And we've been assuming that lambda x, happy x, is the interpretation of happy. The only thing that has changed is now I've gone ahead and made explicit that we're talking about x as a type E expression. It's an individual. Okay. And we do our lambda application exactly the same way as we do before. This says, find something that can function as P. Find it here inside of the parentheses. When you get it, take it and put it in place of this currents of P. Give back the result. Well, there we go. We give back the result. Is happy ends up meaning exactly the same thing as happy. Since that's what we were trying to do, and that's what we now have done, we're happy. You're happy, right? Okay, so next thing we're going to look at is noun phrases. Noun phrases generally, if they're singular, they generally occur with an article. It can either be the definite article, the, or the indefinite article, a. And at this point, we're going to look only at a. We will take the up in chapter 6. So to translate the sentence, Fido is a dog into logic, we need to know how to translate the indefinite article a. What do we do with it? And we're going to take a not very serious proposal. The not very serious proposal is that is vacuous, that it does nothing, that it acts the same way that be and our is act. I say that's not very serious because does tell us something about countability. If you are a dog, then You're something countable, an animal that you can have 10 of, but you only have one of. If you are a dog, then you're probably dog meat. And dog meat and countable dogs are different things. So really is doing some serious work. But the work it's doing is something we're not ready to deal with yet. And so we're going to kind of ignore it and say that to be a dog is no different than to be dog. Okay? That's just so that we can go on and look at other things that we're more interested in. We're doing this so we can kind of put it aside and not focus on it, because we want to focus instead on what happens when we put adjectives and nouns together. And this is something that we have to deal with in order to do that. Okay, now the translation of Fido is a dog. If we assume that Fido translates as Fido, that is translates here as lambda p, p, that has the exact same translation, and that dog translates as lambda x, dog of x. Then our translation of Fido as a dog proceeds like this. I've done it in a top-down fashion. You might prefer doing it in a bottom-up fashion. They all work. So Fido as a dog has two pieces, Fido and is a dog. Of the two, is a dog is the function, Fido is its argument, and so we split it up here. We take the translation of is a dog, we apply it to the translation of Fido. Now, we could go ahead and say that the translation of Fido is Fido. We're going to do that. We're going to save that until the end. We're going to leave it just like this for a long time and work instead on what do we do about the translation of is a dog. So the translation of is a dog, well, this is again something made up of two pieces. It's got an is piece and it's got a dog. Of the two, is a function, and it has to apply to a dog as its argument. But here still we have something that has two pieces. It's got and it's got dog. And before we can apply is to this, we have to know what this is. And so we have to figure out how to interpret it. We take those two pieces, the interpretation, the translation of and we apply it to the translation of dog. Okay. So now we've gotten all the way down from the top level sentence down to all of the words at the bottom. We have the translation of is, we have the translation of we have the translation of dog, we have the translation of Fido. And so now I'm going to start plugging in pieces. I'm taking it very slowly. It's okay to do multiple things in one step, but this makes it a little bit easier not to get lost, not to make mistakes along the way. So we'll only look at this part here. And we have is that's translated as lambda pp. And we have dog that's translated as lambda x, dog of x. Now these are two things that we can put together. This says find something that can act as a P. It has to be of type ET. Well, this is of type ET. What do we do with it? We take it and we substitute it in place of P and give back the result. So this whole thing up here reduces to this. That's what we get by putting lambda x dog x in place of P and giving back the result. Now we do this part. Here we have a function is that can apply to an argument. So we put those two together. The translation of is there, lambda pp. The translation of a dog we've just given. We don't have to change anything. It's already there. And what do we do with it? We take that and we put it in place of p, and we give back the result. The result is the same thing it was last time. It's lambda x dog of x. Now we have a function that can apply to the translation of Fido. This is where we actually go ahead and give the translation of Fido as Fido. We take our function. It says find something that can act as an x. It has to be type E. Fido is of type E. It denotes an individual. And so we can put it in place of x and give back the result. And the result is dog of Fido. Okay. So this is nothing particularly new. It's following the exact steps that we used last week. The exact steps that we introduced when we started out doing these lambda expressions as functions. The only difference is we have a new function, one that takes a function instead of taking an individual. But otherwise, the process is exactly the same. Okay, now we're going to look at adjectives as modifiers. We have Fido is black. That's no modifier. We have Fido is a dog, no modifier. But we also have Fido is a black dog. And here, the word black is acting as a modifier, modifying dog. It tells us what kind of a dog, and that's one of the things modifiers do. They break something into smaller categories, if you will. So it takes all of the dogs and gives back just black dogs, a smaller group. Well, we observe that A and B together entail C. If Fido is black and Fido is a dog, it follows that Fido is a black dog. Likewise, C entails both A and B. If Fido is a black dog, it follows that Fido is black and that Fido is a dog. Our analysis, however, does not tell us, does not give us these observations. It doesn't predict these. And the reason is because we don't yet have a way to analyze this sentence. Why not? Well, let's take a look and we'll see. I'm going to jump ahead. The why not is here. Here we have black, which is of type ET. The AP dominates the A, which dominates black. That makes the A of type AP of type ET. Dog as well is something of type ET. True of dogs, false of non-dogs. That makes the N here of type ET. And the problem is we don't have any way of putting these two expressions together. This is the form of a function. That is, it's a form of sigma tau, something that can take a sigma and give back a tau. But this over here is not that right type. It's not the sigma that's needed. The AP needs a type E expression. This is not a type E expression. So the AP cannot be the function that takes the N as an argument. Can we do the reverse? Can we take N to be the argument? That's over here. This is again type ET. Suppose we try to take this to be the function, something of type sigma tau that requires something of type sigma. Well, this sigma matches up with this E, meaning the n needs to have something of type E. But again, the AP is not of type E. So those two things can't go together either. So here we have a situation where we're stuck. I've set up here, in both cases, the n bar is undefined. That means we don't have any rule that tells us how to put these two expressions together that will give us a new expression of an understood type. Since black dog is a perfectly fine English expression, we have to do something to change our analysis. And there are two solutions that people have given. One solution is to change the type of black. We could have chosen dog, but black is usually chosen instead. This black is of type ET, and we've seen that that makes this of type ET, and that means that it can't combine with something over here. So we change the type of black to something that can combine with the ET type dog. Okay, the other solution is to add a new rule. Our only rule so far has been function application. And we've just seen that function application doesn't work here. Well, suppose we added a new rule that made it possible to put these two things together. Not function application, some other rule. Well, then we could, at least in principle, get something up here that is defined. Get something, say, of type ET, which is what we actually want. Okay, so let's go and look through those two solutions. The first one is called the type-raised adjective solution. And you'll see why that is the case pretty soon, but the idea of type raising is to take black, which is so far only been of type ET, and to turn it into something more complicated. And this is what that something more complicated is, and we'll calculate that type in just a minute. So this says, take black to be something that first requires a one-place predicate. And it takes that one-place predicate as its argument. That's going to be the word dog, the translation of the word dog, okay? Then give back this. And that is itself a one-place predicate. And we'll deal with that in the next slide. But just looking at this part, lambda p e of t, I'm sorry, lambda p sub et, that tells us that black, this new black, is a function whose first argument is type et. And from that, we can go ahead and give part of the information of what type this expression is. It's a type that takes something that's going to be of type ET and it gives back something else. Okay? What that something else is, we're going to get by looking here. So let's go to the next page. After it gets its, I've repeated this because I want to be able to refer back to it. After it gets something of type ET, the next thing it says is, give me something of type E. Okay, that means we have another function that takes an E-type expression and is going to give back whatever this is. That gives back, we get a function back that takes an E-type expression and it gives back something else, whatever this is. Finally, after we give it that E-type expression, we get back a formula, the highlighted formula, And a formula is something that's either true or false. So its type is T. So that means we can see that what goes into here is type T, and we end up with a final type for this new translation of the word black. Okay? Now, if you're like most people, you don't immediately see how this is going to give us the right results for, say, black dog. So let's go through and show it. We'll start with our assumption that we've got all along, that dog is this predicate, lambda x, dog of x. Okay? And now we've defined black in such a way that it can be a function that can take that kind of a thing as its argument. And so we can put these two together by function application, which I abbreviated FA because it was too long to squeeze in here otherwise. So let's go ahead and plug in our pieces. The translation of black we just gave from on the previous slide is here. Lambda P of type ET, lambda Y of type E, black of Y, and P of Y. Dog translates to this. And we do here what we always do. This says find a one-place predicate that can substitute for P. You find it here, and you put it in place of P. Then you give back the result. That's everything between the brackets here. That result is here. Instead of a P, we now have lambda x, dog of x. Okay. And here we have a function that contains something else that involves a function applying to an argument. So we can reduce or simplify this part as well. This says find something that will play the part of x out here. When you find it, substitute it for x and give back the result of this with that substitution made. Well, that's dog y. Everything else here stays the same. This doesn't change. This is exactly the same as what we had above. Okay? So we have black dog translating as lambda y, black of y, and dog of y. Then the next thing we're going to do is combine that with and then we combine the result with is. But those two expressions were vacuous. They don't change anything. They take something and they give it back. And so I'm going to just very simply ignore those steps and say that is a black dog translates as the same thing as a black dog, which translates as the same thing as black dog, which is the same as what we just calculated here. Okay, so now we have Fido is a black dog, and that's going to be what we get by taking is a black dog, its translation, and applying it to the translation of Fido. This time I'm going to do both at the same time. Is a black dog we just calculated. That's here. The name Fido translates as the predicate logic name Fido. And now we have something we haven't seen before, but it's not very different from what we have. This says, find something to translate, to substitute for occurrences of y. Find that something out here, make sure it's type E. Fido is of type E. and substitute it for y, for all occurrences of y in here. And what's new is that this time we have two occurrences of y. There's one here, and there's one here. Okay, not earth-shattering, ground-shaking stuff. This is follow the instructions, make the substitution. In this case, you substitute 2 times. You get black Fido and dog Fido. Okay. Now, one of the things that's good about this analysis is this final result, because black Fido is the translation of the sentence Fido is black. And dog Fido is the translation of the sentence Fido is a dog. Now, if you want to go through those by going through the slides separately, I've actually given the analysis of Fido is black here, and this is the result of doing that analysis. Okay. And I've given the analysis of Fido is a dog here, and this is the result of that analysis. Okay. But what's important for us is that we now have this result. Fido is black and Fido is a dog together entail Fido is a black dog, because Fido is a black dog just conjoins the translation of B with the translation of A. And we also get the reverse entailment explained. Okay. Okay, so we did that, but we did it at a cost. We decided to try a new translation for the word black. But that new translation for the word black is going to cause us problems itself if we try to use it everywhere. In particular, if we look at the sentence, Fido is black, what happens if we use this new black here? Can I get it? I cannot get it. Okay. Yeah, we go. I got it. Okay. What happens if we use that new definition for black? It's of type ET. That makes the AP of the same. This says take something of type ET as an argument and give back something of type ET as a value. But this is not of type ET. Or we could try the other way around. This says take something of type ET as argument, but that isn't of type ET either. So these two things can't go together at all. And we end up with something undefined. Now, the earlier definition of black, we already saw, that worked perfectly fine. It was just of type ET. It had no problem combining with is. So what we'll need to do, if we're going to take this assumption, is we're going to have to assume that there are 2 different meanings for the word black, 2 different translations. One of them is the simple one that we started with, lambda x, black of x. That's the one that goes together with the word is in Fido is black. And one of them is this new fancy complicated thing, which is what we use to combine black with dog. Okay. Now that looks like a not very desirable thing. Why do we have to give 2 different translations for one English word? And it's maybe not the best possible situation to have, but it is a systematic, uh, it is something systematic. It's something that works for whole classes of adjectives. It works for black, it works for red, it works for tall, it works for happy, it works for a lot of adjectives that we've seen. What's more, we don't really have to list two different things in the lexicon. We could list one of them, let's say list this one in the lexicon, and add a rule that tells us how to make a new meaning out of it. Then if we have 100 adjectives, that 100 adjectives plus one rule gives us 200 translations. The original translation and the translation that we get by applying that new rule, okay? And down below, we can see how that rule would work. The rule is, if you have something like black 1 here, you can plug that meaning into here to create a new something, a black 2. So this, we've given all of the kind of extra bits here and here that are needed to make all of that work. We plug the translation of black 1 here. That is this. When we apply it to our y as an argument, this y substitutes for this x, and it gives us back black y. And everything else comes down the same, and we end up here with black 2. The same thing that we calculated that we wanted to have up here in order to combine with the translation of dog. Okay, I give it here as a generalized solution. It says for any adjective, adj, of type et, there is an et type adjective, adj2, having the same form as adj, so black to black, white to white, happy to happy, where the translation of adj2 is given as this, where we put the original type et translation of adj into there. We just did that for the words black, word black. There I call this black 1. Here I don't have a 1, but that's an unimportant difference. This is saying that we can make a second adjective out of a first adjective and just by plugging the first adjective meaning into this and giving back the result. We can think of this as a type changing rule. It takes one adjective, which was of type et, and essentially changes it into another adjective of type et. It actually creates a new adjective of that type, but it's like as if it's changed the type of the adjective. And so this kind of a rule is called a type changing rule. And in this case, the new type, et, is a higher type, a more complex type than the type et. It contains the type et as a part. Okay, so it has to be more complex. A more complex we call higher type, and going to a higher type is raising the type. So we call this also a type raising rule. Okay, so that's the end of our first solution for what to do in order to put the word black together with the word dog. We promised the second solution. The second solution was to add a new rule. They kept their type simple. We don't change the type of black. We don't change the type of dog. We keep them both as type ET, but we give a new rule for putting them together. And that new rule is called predicate modification. And here's how it works. Suppose we have a word like black and another word like dog, and each of them is of type ET. Okay? This new rule tells us how to make a meaning out of those. It says start with a lambda z, where z is of type E. It's an individual. Apply the translation of P to Z, and conjoin that with the result of applying the translation of Q to Z. Okay, this is a new rule. This is unlike anything we have ever seen until now. Importantly, it is not just another way of doing function application. If we put P and Q together in this way, that's not the same as applying one of them, the interpretation of the translation of P, to the translation of the other. It's not the result of taking the translation of Q and applying it to the translation of P. It's something different altogether. It's just a different rule, okay? So if you get the situation where you have two one-place predicates going together, do not put them together like this. Do not put them together like this. This is a completely separate rule that we use instead of that rule of function application. Okay? I say this every year. Every year somebody tries doing it this way. Okay, it's going to happen. I know. But I've warned you. Now it's your fault, not mine. Okay, so let's see how this works. We're going to keep to a very simple black. Black is the one-place predicate black. Takes an individual, gives back a formula. Dog is also a one-place predicate. Takes an individual, gives back a formula. Our rule of predicate modification tells us we can put those two together just like they are, like this. We put the lambda z here, it's of type E, and we make a conjunction. The first conjunct we get by taking black, translating it, and applying the result to z, conjoined with, and the second one we get by taking the translation of dog and applying it to z. That is our rule of predicate modification. That's what it tells us to do. Now we do substitutions. In place of the translation of black, we put the actual translation. Okay, in place of this, we give the actual translation of dog there. Now we have two more things that are the form of a function applied to an argument. This is the function. This is the argument. We have to take the argument, substitute it for the occurrence of x here, and we get lack of z. Here, we do the same thing. That's a function, applies to the argument z. It says put z in place of x, give back the result, dog of z. So what do we get back? We get lambda z sub e, black of z, and dog of z. Now let's just look back and see how that compared to what we had before. What we got in our previous the previous time, yes, I do have to go back up here, was this, lambda y, black of y, and dog of y. That is the exact same thing except for one difference. This one uses y here, here, and here. But our new translation puts a z in those places. We have a z here, and here, and here. But we can tell that that difference really doesn't matter because the two functions do the exact same work. They both say, find something that can substitute for a variable. When you find it, put it wherever you find that variable. It doesn't matter if we use z to identify that variable or if we use y to identify that variable. As long as it's telling you to do the same work in the same way, the choice of variable doesn't matter. We could use x, we could use u, you can use v, you can use anything else that you're comfortable using as a variable for an individual. The rest of the calculation is the same as it was before. Is a black dog is going to be translated as the same thing as a black dog, which translates as the same thing as black dog. And so Fido is a black dog takes, oh, and I made a change that I didn't mean to. It takes the meaning of is a black dog, which is this, although I had Z and now I've changed that to X. I'm sorry. Like I said, it doesn't matter. And that's why I made the mistake. If it were Z, it would work just as well. It says find something to substitute for this variable. You substitute for the variable here and here, find the something there, and you end up with black Fido and dog Fido. So we end up with the same result, but we end up with that result in a very different way. Okay. Okay. The next thing I'm going to look at is relative clauses. We're not going to actually analyze relative clauses in detail. We're not going to show you how to give them the meanings they have, but we will give them meanings that we can use, okay? Because relative clauses work very much like adjectives. We have, for example, a dog that is black. That really tells us the same thing as a black dog. If I say Fido is a dog that is black, I haven't told you anything different from what I told you when I said Fido is a black dog. This relative clause can do things that sometimes a simple adjective can't. So you can say a man who feeds Fido, but there is no way of turning that into an adjective modifying a noun. You can do a toy Fido plays with, okay? Fido plays with is acting like an adjective, but it can't actually be turned into an adjective. It's not like black, and that is black. But we're going to go ahead and give a way of analyzing these two. And the ways of analyzing them are going to be just like the ways of analyzing one place, just like the ways of analyzing adjectives. Okay. One of the ways of doing it is to take a relative clause to be a one-place predicate. of type ET, right? That is black will be a one-place predicate of type ET. Dog is also a one-place predicate. So in order to put dog and that is black together, we'll have to use the style that combines two one-place predicates. That is, we'll have to use predicate modification. Okay. The second way we'll spell out is just like the second way for doing black. That takes a relative clause to be type ET. That makes the relative clause something that can act as a function applying to an ET type expression, like dog, for example, to give back an ET type expression, dog that is black. And it'll do that using function application. So this is not really going to be anything new. It's going to be the same thing that we had before, extended now to apply to relative clauses. Okay, so how do we give these relative clauses? Well, the basic idea is that we take this that is black to be like a sentence is black. That's missing the, it's missing the subject. It's missing whatever it is goes in here. And we're going to take that missing piece and turn it into, we're going to turn it into an X. And we're going to bind that X with a lambda X at the front. Okay? To do this properly will take weeks, 3 weeks or so of spelling out all of the details. That's for an advanced class. For this class, we're going to do it simple. Okay? We're going to say, this is what we need, so let's just give it. Okay, here we have who feeds Fido. Up here, we ignored the that. Here, we're going to kind of ignore the who, but we're still missing an actual person, the one who feeds Fido. Okay, so that is going to be a variable, X. And that's going to be bound by this lambda X here. The lambda X is essentially the work of the word who, but we're going to just ignore that. Okay. So we got a lambda X, feed X, Fido. Fido plays with, like the toy Fido plays with, we're missing something, well, between here, between the H and the bar. We're missing an object, what it is that Fido plays with. We're going to put that object as a variable, and we're going to lambda bind it. Okay? So this is our analysis one. It's the simple one. It's the one that takes relative clauses to be one-place predicates, and these are those one-place predicates. So if we try now to look at the expression, a dog that is black, we have dog here, and we have that is black here. We put them together with predicate modification, just as before. Predicate modification says add a new variable, lambda z, take the translation of dog to apply to z, take the translation of that is black to apply to z, put the two together with an and then we do the same calculation that we did before. We spell out the translation of dog here. We apply it to z by taking the z, substituting for the x, and we get dog of z. We take that as black. Its translation applies to z. Its translation is here. It applies to Z by taking Z and substituting for X, and we get black of Z. Those were all done inside of these outer brackets, lambda Z E with those brackets. And so we keep that part unchanged here as well. And we have a new one-place predicate. Okay. And just to show we get the exact same result using the other alternative analysis, we give that here. The other alternative analysis takes that as black to be just like the second analysis of black. Rather than just a simple predicate, this is a function that combines first with a function by function application, and then gives back this as the result, where that function is plugged in place of P. So in this case, dog that is black has two pieces, dog, and that is black. That's the same as before. But this time, that is black translates as a function that can apply to the translation of dog. So this time, we have to combine them by function application. It works like this. This is a translation of that is black. It tells us to find something of type ET that can substitute for P, for this P. You find something here. You take that and you put it in place of the P. You put it in place of the P to give back the result. And here in this result, we still have a function that still has to apply to an argument. We take that argument, we put it in place of the variable being bound by the function, and we give back the result. Lambda y sub E, black of Y, and dog of Y. So once again, the result of our new analysis that takes that as black to be a function that can apply to the translation of dog as an argument gives the same result as the other one. The same result, except that we have different variables, Z here and Y in the other one. So just like we could have two different ways of analyzing the adjective black, we can have two different ways of analyzing the relative clause, that is black. And we could do the same thing for the relative clauses, who feeds Fido and Fido plays with. We could give a second analysis exactly parallel to this analysis for black. The only difference is, in place of black here, we would put Fido plays with, plays with Fido X here. Instead of black X here, we would put, what was the other one? Who feeds Fido? Feeds X Fido